This is lecture 14, where we'll be looking at higher order Taylor series and the Runge-Kutta method for solving initial value problems governed by ordinary differential equation. Now, in the previous lecture, we have looked at three techniques to solve ODEs, basically the Euler method, the Hume's method, as well as the midpoint method. So the Euler method, if you recall, it is derived based on the Taylor series, and we call it a one-step method because we use whatever we know from the current step to find out the solution for the next step. So from your Taylor series, if I expand out the Taylor series for the point yi plus 1 using the point yi as my reference point, with Taylor series, we are going to take the first three terms. Okay, so basically on the left hand side, you have yi plus 1 is equals to yi plus h times yi prime. So the terms at the other end, we assume them to be 0 because our Euler method is a first order method, meaning that we are only taking the first three terms. Okay, now you might wonder, why do we restrict ourselves to the first three terms? Can we actually increase the number of terms that we have from our Taylor series as a way to improve the accuracy of our solution? So technically you can. Okay, so instead of using the Euler method, technically you can say that rather than taking the first three terms, I'm going to take the first four terms or five terms, for example. Okay, if you do that, it means that theoretically, if you look at the expansion here, you would have a higher order accurate solutions compared to the Euler method. But this would require you to know the knowledge of yi prime, yi double prime, and yi triple prime. And this can pose a problem, which I'll show you from an example. Okay, so let's say you have this particular example. You have dy dt is equals to minus 2t minus y, and the initial condition given to you is y at t equals to 0 is minus 1. So let's say you're going to solve this ODE using the fourth order scheme. So what is the fourth order scheme? So let me rewrite the Taylor series expansion, but instead of yi plus 1, I'll say y at t plus h. So h is the step size, t is our current time, which essentially is your yi plus 1, and this is equals to y at t, which is your yi, plus h y prime. And because we want fourth order scheme, it means that we want our Taylor series to be of order h to the power 4 accurate. So it means that we are going to take this term y double prime h3 3 factorial y triple prime, and this would be accurate up to h to the power 4. Okay, so to get a fourth order scheme, we would need to take terms up to y prime, y double prime, and y triple prime. So let's say we want to formulate our numerical method based on this set of terms here. Okay, so we already know that y prime here is dy dt, and dy dt is already given to you, which is your minus 2t minus y. Okay, so what is y prime? Y prime is minus 2t minus y. So now we need to know what is y double prime. So what is y double prime? Y double prime would be given by the derivative of y prime, which I can write it as d dt of y prime. Okay, now if I differentiate y prime with respect to t, this would give me minus 2 minus y prime. Okay, and what is y prime? Y prime is given by this first equation. Now if I substitute all of this into my y prime, my y double prime would be given by minus 2 minus plus 2t plus y. So that is my y double prime. So I can do the same thing for my y triple prime. Okay, so for y triple prime, it is just the derivative of your y double prime with respect to t. So if I differentiate y double prime with respect to t, I'll get 2 plus y prime. Okay, and what is y prime? This is y prime. If I substitute them back into here, I get 2 minus 2t minus y. Okay, so right now, in order for you to find the value of y at the next step, and since you already have y double prime, and y triple prime, you can find yi plus 1 to be given by yi plus h. So here you would have minus 2ti minus yi plus h squared over 2 factorial minus 2 plus 2ti plus yi, and then you have the third order term and your y triple prime. Okay, So this is your general formula to solve this ODE using a scheme up to 4th order accurate. And you can solve this by setting I equals to 0, find the values of T0 and Y0, and solve this until you reach the time step that you want. So technically or theoretically, you can include higher order terms to improve the accuracy of the solution, but there is a problem to this. First of all, you must derive what is y double prime, y triple prime, and all the higher order terms depending on how accurate you want it to be. So this can be problematic if the expression on the right hand side is very complicated. If it's too complicated, trying to differentiate it is going to be a problem. Secondly, because you need to find your y prime, y double prime, y triple prime, and so on, it is not easy to generalize this into a numerical algorithm that can be implemented for all kinds of problems, because for every single problem you will need to differentiate, or you need to derive what is your y double prime, y triple prime, and so on. So there's no way for us to actually generalize this into a general numerical algorithm to solve the ODE given. So although theoretically we can improve the accuracy of the Euler method by including higher order terms, the approach is not practical, and it does not present itself as a generalization of a numerical algorithm. So in the next part of the lecture, I'm going to explain to you what Runge-Kutta method is, and Runge-Kutta method allows us to generalize uh, the calculation or the estimation of our higher order derivatives here in terms of a weighted average value.